Welcome. Welcome, everyone. It's a real pleasure to have you all here this evening for such a special event. My name is Jean-Paul Kneib. I'm professor of astrophysics here at EPFL. I'm also leading the EPFL Space Center. And I want first, before entering into the real event, I want to thank people that have been organizing with me such an event. And I want to give a special thanks to Joris, Annika, Estria, Candice, and Martin, and some others that I forgot the name. But they're here behind, like the people doing the controlling of the video and stuff. So welcome. I have also, of course, we have our 2 Nobel Prize here, but to help making this event success, I have also with me on stage Galactic Chloe, that some of you know, I guess, because I see many students here. And as you know, or you may not know, she's an EPFL student finishing her master, and soon she will fly out and maybe to the moon.
Hopefully.
Right, and then next to me, I have Richard. Richard Anderson is a new professor, junior professor here at EPFL. He's been key for making this event because he has a good idea to invite Jim, one of our Nobel Prize here tonight. And maybe I'll say a bit of your words of presenting Jim. He's an ERC grantee. It's one of these very prestigious European grants to do K research, forefront research. His ERC project is called IPSTARS, and the idea of the project is to measure distance in the universe. And once you know distance in the universe, you can do a lot. And in particular, you can measure the expansion of the universe. And so that's one of the things Richard is doing. So I will introduce first Michel Mayor. So Michel, come on stage. So Michel knows Lausanne because he was born here in Lausanne. Okay, he even did physics studies in Lausanne at University of Lausanne. But then, of course, he moved to University of Geneva to do his PhD back in the end of 60s, beginning of 70s. And at that time, students, you look and you learn a lot of things. And one of the key things that has been doing, and along the years up to the main discovery, was to probe the motion of stars with one technique, which is the radial velocity measurement technique. And when you do that with great detail and super good accuracy, you're sensitive to the motion of stars, and the stars oscillate. And if you find such a star oscillating, then you can say, oh, maybe there's a planet around it. And that's his famous discovery back in 1995, well, the discovery of the first exoplanet. And today, there's about 5,000 of them that have been discovered. And I think we can say rightly that you have opened a big new field of research in astrophysics. And that's also why you got the Nobel Prize, and I want to thank you again. So now Richard will take the work to introduce Jim. Jim, you can go on stage.
So there is an old saying that as scientists, we're standing on the shoulders of giants. This proverb emphasizes that scientific inquiry builds on previous insights to break through new barriers and identifies, of course, the giants as those thinkers who have particularly shaped and defined our understanding of nature and science. Professor Philip James Edwin Peebles was born in St. Boniface in the Canadian province of Manitoba. At the University of Manitoba, he fell in love with physics and this eventually led him to Princeton University, where he obtained his PhD in 1962 and has spent his entire career since then. He transferred to emeritus status in 2000 and remains the Albert Einstein Professor of Science there. Over the course of his scientific career that spans more than 6 decades, Professor Peebles has transformed the study of physical cosmology from speculation to precision science, which now forms an integral part of our understanding of physics more generally. Professor Peebles' discoveries provide large parts of the common basis that cosmologists and astronomers build upon today to better understand our place in the cosmos, and he has indeed contributed to some of the most fundamental insights into the origins and the evolution of the universe, from the Big Bang to the galaxies that we observe today. For example, he has made fundamental contributions to Big Bang nucleosynthesis, which explains the way that we have heavier elements than hydrogen in this universe. He also predicted the existence of the cosmic microwave background, which is a ubiquitous radiation that surrounds us in all of space, and that is the most important observational window into the early universe and how it was in its very early stages. And these insights provided, of course, the physical explanation for how to interpret this radiation emitted nearly 14 billion years ago. And this radiation, of course, often is called the echo of the Big Bang. One of the most remarkable consequences of this work is that we live in a universe where all of the ordinary matter, this includes all the stars, all the gas, all the dust, and all of the galaxies, makes up only about 5% of the energy content of the universe, or about, turned in a different way, saying that 80% of all matter cannot be directly observed and is called the dark matter. Of course, Professor Peebles has been awarded many prestigious prizes, but as he told me on Monday, one of his very favorites is the Order of Manitoba, awarded by his home province in Canada to honor residents who have demonstrated excellence and achievement and enriched the social, cultural, and economic well-being of the province. Of course, in 2019, he has also been awarded the Physics Nobel Prize. So with cosmologists and astronomers today routinely using his ideas as they're conducting their research to better understand the cosmos, and often actually just abbreviating the ideas with acronyms like the CMB, CDM, LSS, BBN, it's very easy to see that we are standing very much on his proverbial shoulders, and that, differently put, Jim Peebles is a giant of science. I'm so very delighted to have you here today, and I would like everyone to very warmly join me in welcoming you here today.
So in a few seconds, Jim will come here and do his presentation. Just stay on stage. What we're going to do after the presentation of Jim and Michel is that we're going to have kind of a round table where we have some prepared questions to ask them. But after, everyone you in the room or following on YouTube, you can ask questions on Slido. So if you go to sli-.do, sorry, you can connect with the hashtag Cosmos, and then you can post your question. And you can do that already now. And you be able, during the presentation, after the question, to also rank the questions. So, Jim, it's your turn.
Thank you.
Come on stage.
Richard, thank you for those kind words. Colleagues, ladies and gentlemen, I propose to begin by making a statement about what natural science is really about. At its core, it is the study of what we see around us, the attempt to make sense of what we see, and to understand how that relates to our existence. It's what you all do, but a natural scientist will get compulsive about this and looking at lots of details. So I begin this introduction to the world around us by showing, if we will show, what shall I do now? Well, absolutely nothing can go wrong. Good. This is an image of historical interest. You may see the date 1967. Is that, yes, 67. Of course, that image was no surprise. We all knew that the world is round. But it's quite a different thing to see the round Earth. This image made a great impression on people, not because of the discovery that it's round, but by simply looking at it, you have the intuitive feeling now that this is a beautiful place, it is a very limited size, and it does behoove us to take a little better care of it. I saw an example of the effect of that image. The image in the center is the same one. It is a publication by Stuart Brand of hand tools. It must be, well, that thick. Page after page of hand tools. The thesis was what we would now say develop sustainable lives. The movement to try to make the world, take better care of the world, was greatly influenced by that picture. We have more galaxies in our, or more planets in our solar system. Here is Mars. I will be speaking later about the idea that there may have been life on Mars. When I first saw this image, wow, it's an old stream in the peninsula. At one time, Mars was a very different place. Perhaps there was life back then. We can be pretty sure that there isn't much happening now, but just so fascinating to see another world and to see that things have happened on it, some parts of which are familiar, some quite new to us. Here is the next planet out, Jupiter. It has about the composition of the sun. Most of it is hydrogen and helium, trace elements of the heavier elements of which we're largely made. It has the composition of the sun, but it doesn't shine like a star because the pressure isn't high enough to drive the nuclear reactions that generate energy that must filter out. But it is still cooling off from its formation. There are eddies of warm material moving up, cool materials moving down. Those eddies are moving in a planet that's rotating, that twists the eddies and produces these marvelous patterns across the planet. Here's our sun. You see on the right a detailed image of the surface. It's again convecting and making a pattern. You may have observed this if you were cooking a soup that's pretty thick. And as the soup heart pots rise, they make this pattern on the surface of your pot. A similar thing happening here. On the left, the whole face of the sun, sunspots, and that's where a magnetic field, I should put, never mind. A magnetic field is suppressing this convection. It's a cool spot. The sun is a star. It's not alone. Here is a map of the nearby stars. The sizes of the images are to scale. The sun is here. This is a much bigger star, that a much smaller star. The colors are meant to be realistic. The sun has a temperature that makes its surface look sort of yellowish. Sirius A has a mass twice that of the sun. That heavier pressure by the double the mass causes it to shine far more brightly. It will exhaust nuclear fuel far before the sun does. When it does, it will lose a lot of material and form a little white dwarf. You notice this dot is a white dwarf that was originally a star even more massive than Sirius A that died sooner and left that little remnant white dwarf. It's very small, it's very compact, but its mass is more like the mass of the sun. You notice that there are a few stars in this system that are bigger than the sun, but most are much smaller, down to tiny little fellows here and there. Approximately, just, I don't know whether you can see, oh yes, a little red dot here. My colleague Michel may tell you some interesting things about it. Well, You may have observed the Milky Way, a splash of stars running across the sky. It is, in fact, the distribution of stars in our galaxy, which is shaped like a disk. And we are in the disk. When we look along the plane of the disk, we see lots of stars. When we look away from the disk, we see fewer, as you see in this image. You see dark lanes running through the stars. That's not the absence of stars, but rather the presence of dust. Here's another galaxy, this one a short distance away from us, relatively speaking. It illustrates to me one of the joys of astronomy, something we can all... I look at this and I feel, isn't that beautiful? I don't care about the science. It's a beautiful thing, which is rather curious because we all evolved as a species never seeing that, yet we see it for the first time, and many of us are deeply impressed. You notice blue spots. That is where stars have formed recently. The most massive of them, like Sirius A, are very hot, they're very blue, and they're shining brightly. The bright shining light from these stars can ionize the interstellar gas and make these red spots. That's where the main element in the interstellar medium, hydrogen, has been ionized. It's shining because the plasma is recombining and making a red spot in the making a red region. You see the spiral arms running in, and you notice the lanes of dust making this elegant pattern, and you notice in the center a little concentration of light, much. You also notice a yellow glow here. The color rendering is such that you can't tell it, but that yellow glow is all the way through this galaxy. That yellow glow is the light of some, 10,000 million stars like the sun. Astronomers tell us, and Michel will assure us, that many of these stars have planets. Maybe there are as many planets as there are stars. So there is in this nearby galaxy some 10,000 million planets. It's an excellent bet that all sorts of fascinating things are happening on those planets, and it is guaranteed that we, the human race, will never get to see what is happening. This is just a sobering note of our position in the world. Let us go on. An expanded view of the central region shows this image. You notice the spiral arms running right into a little hot spot. That's a clump of stars with a mass of 1 million times that of the sun. It's kind of particularly fascinating because in our Milky Way galaxy, there is in the center a black hole with a mass of 4 million times the mass of the sun. Perhaps you've seen in the newspapers the image of that object. It's a black hole. Lots of fascinating questions. How in the world did that black hole form in there? We won't get into that. We'll only pause to admire. But there's a little clump of stars, and does it contain within it another black hole? I'd love to know the answer. One of the nice things for a scientist about astronomy is that there's an endless list of wonderful things to think about. So let's go on and notice that there are many other galaxies. Examples are shown here. The two main types, disk galaxies, some of them quite flat, spirals or ellipticals like this little guy, indicated where there are some of them. These are two views of the distribution of galaxies in our immediate neighborhood. The one on the left is showing what you see if you look out there and map the positions. The one on the right is what you would see if you went 90 degrees and looked from the side. You see in both the concentration of stars to a plane. We live in a sheet of galaxies. We can look in larger scale, and we see this. This was taken, I'm particularly fond of this image because the data for it were taken by an astronomer, Donald Shane, from the late 1950s through the 1960s. 10 years of his life was spent counting the positions of the million nearest galaxies. He had big photographic plates, he had a traveling microscope, and he would scan along and see, here's a galaxy, here's a galaxy, here's a galaxy. He often did that while he was director, and he would be, as he was entertaining a visitor, talking to the visitor and then turning and counting a few galaxies. And I bet that the more tedious the visitor, the more time he spent scanning the plates. These data were taken with such great care that when fast computers came along and the ability to make images, we were able to take his data sheets and digitize them and make this image. And one of the deepest pleasures of my life was taking this image and showing it to Donald Shane and asking him, so is this what you saw? He laughed and said, I was looking at this one galaxy at a time. This is the world around us. You may have noticed the enormous numbers of planets around stars in each galaxy, the enormous numbers of galaxies. We are in a very large, large world. We are a small part of it, but a real part. And I propose now to stop and let my colleague, Michel speak about investigations of what might be around some of those stars.
Thank you, Jim. So, now, look on this billion of probable planets. So, today we have the pleasure and the privilege to have the chance that the technology offers the possibility to study what is called this old world. So, yes. If we are looking only a very, very small piece in the center of the galaxy, I don't know, very, very small angle. In fact, this is typically what we have seen. And typically, this is the question, how many planets are orbiting this star here, or this one here, and so on. Do we have the capabilities, the technical possibility to detect exoplanet orbiting this star? The problem is not to discover new stars, because you see you have plenty of stars. Stars, something similar to a sun. So it's interesting to have a look back in the literature of the last century. It's very strange that during the first half of the century, astronomers do not believe we have other planetary systems in the Milky Way. You can recognize here some very important names of astronomy, and all the evaluation made at the time conclude that we should be alone in the Milky Way, or maybe you can have few, very few. And this was based on a very narrow theory. It's the problem of the close encounter of two stars. So to form the nebula around a star, to form planets, at the time people believed that you need to have a close encounter of two stars. So by tidal effect you can create the nebula, and that this will be the place to form new planet. But you know that the probability to such an event is almost nothing, negligible. Billion of stars during billion of years, no close encounter. So this is the reason why the very erroneous and pessimistic evaluation during the first part of the century. And suddenly, in the middle, all the estimates change due to the change of paradigm. And if this was tidal, the explanation was based on the tidal interaction of two stars, here, the view is completely different. It's because at the formation time of the stars, the collapse of the cloud always have an excess of angular momentum, and so the excess of angular momentum is stored in the nebula, the accretion disk in modern term, and this is a place to form new planets. And this is a very important change because this is a completely byproduct of the stellar formation. So this is exactly the reverse. The probability to have planetary system is almost 100%. Almost every star should be associated with the formation of an accretion disk. And you can notice here that you are at the level of few billion, few 100 billion of planetary system, and this is completely coherent with the modern detection. The change of ideas went in a very small letter published by Otto Struve in 1952. He start for a very a priori different kind of conclusion. If you are looking at the rotation, the own rotation of stars at the lower main second, so stars with mass below the sun or approximately, you remark that they are all slow rotators. And if during the contraction of a cloud you have an excess of angular momentum, you expect very fast rotators. And it is not the case. And Otto Struve concludes this is the origin of the excess of the accretion disk, the nebula, because this is the place where you can store the excess of angular momentum. And this is a small few sentence of this paper, and he said at the end, therefore there can be many planet-like objects in the galaxy. This was a real good conclusion. And immediately after, a lot of work was made on these ideas. And the first hint of the presence of this kind of disk was based on the discovery of the excess of infrared light. If you have the stars emitting light, and you have a disk of dust, the temperature of the disk is lower than the temperature of the star, so you have an excess of emission of infrared light. And this was detected already from the 70s. This diagram is not the first one. And you see that here, this is the light emitted by the star, but here, this is the infrared emitted by the disk of dust. So this was detected, and evidently this is only for young stars. And more recently, the space telescope, the Hubble Space Telescope, looking some young stars here going out of the Orion Nebula, stars with an age of maybe 3-4 million years, so young, 1,000 times younger than the Sun. And if you look with the high resolution, optical resolution of the space telescope, you see that all these young stars are surrounded by the disk of dust. And this was a direct image of the nursery where you can expect to have formation of planetary system. And this was made in 1995. And at the same year, we have started the measurement of the velocity, the change of the velocity of a large sample of 142 solar-type stars known to be single, but with the precision of a new kind of spectrograph we have developed with some colleagues, that in fact we have detected that one of these stars has a periodic change of the velocity with a period of 4.2 days, but the mass was about half the mass of Jupiter. So this looks completely crazy, because the theory at the time was expecting for giant planet like this one, Jupiter-type planet, to have period in excess of 10 years. So 10 years is about a factor 1,000 larger than 4 days. So this was a big doubt of the reality of this effect. So this was the reason why we have decided to postpone the publication by 1 season to be sure that we have exactly the same phenomena the next season. We have, and after the next season, we observe the same period, the same amplitude, and the same phase. So we start to be convinced that it should be a low mass object orbiting this star. And today, using not only the same technique, but part of them with the change of the velocity, we have something like more than 5,000 exoplanets detected. I will describe the other technique having contributed to this. But evidently, we are immediately facing the questions, if we have a discrepancy by 1,000, what is the reason for that? Because to form a giant planet with a Jupiter mass, you need to agglomerate ice particles because you don't have enough silicates and metals in the disk. So you only have ice particles in the outer region of the disk, and evidently this corresponds to a long period orbit. So what is behind this change of observations? So people have tried to analyze what happens when you have a disk of dust and gas with embedded in this a giant planet orbiting this. And you can detect that you have the formation of a density wave, excess of material in some place of the disk here, and the reaction of this excess of matter will change the orbit of the young planet. And the net result of this will be a spiraling of the young star toward the center of the system. This is the explanation of the short period of 51 peg. You can also notice that this effect was already studied and predicted 15 years before the discovery, but the people involved in the search for planet have not read this paper because this paper was mostly devoted to the study of a young galaxy embedded in the disk of a large galaxy. So, if we made a jump of 15 years, and you are in the Altiplano at 5,000 meters north of Chile, you have something like 60 dish of 12 meters, looking at the same time, the same place of the sky, and you combine in a clever way the radiation received by the 60 dish to have a very, very high resolution in submillimeter long wavelengths. And if this kind of instrument is a perfect tool to analyze the formation of galaxies, formation of stars, formation of planets, and the matter in between the different objects. So immediately some colleagues have analyzed and looked on clouds of gas where we knew that we have some very young stars embedded inside. And the net result of this study was to realize that all the disk surrounding this kind of object was exactly with the same structure you have seen previously, that we can see here the formation of planetary system. So today, we already have the capability, technical capability, to analyze the structure, the evolution of accretion disk to form a new kind of planetary system. Going back to my own domain, so the domain is very simple in the idea. If you have a star with a planet, the star emitted a lot of lights, the planet only reflects a tiny part we see from the star. Just an example, the ratio is about 1 billion for the Earth and the Sun in the visible. Jupiter is not better. So, at least at the time, the direct possibility to look for planet was not possible. So the only possible was to use indirect technique. If you have the star here, the planet orbit here like this, you cannot see the planet, but you can have a chance to see a very small wobble of the velocity of the star due to the interaction of the planet. Evidently, due to the fact that the mass ratio is large, it's very difficult to detect with a very small change of the velocity, so you need to have a relatively precise instrument. And just to have an idea of the technical difficulty, this is the spectrum of a star quite similar to the Sun, to the spectrum of the Sun, obtained with a large spectrograph developed by my colleague in Geneva. So this is a very small part of the spectrum. It's about 1/10 of the spectrum. And you see the huge forest of atomic transition you have. And due to the Doppler effect, evidently, we can expect to detect the very small oscillation of this forest of atomic transition. But just to have an idea, let's imagine you would like to detect the wobble induced by the Earth on the Sun. So the motion of the Earth is about 10 centimeters per second. So 10 centimeters correspond to much less than 10 minus 3 of the thinness. You see that you have atomic transition here, and it is about less than 10 minus 3 of these waves. This is the fact. You need an instrument with an exquisite precision to have the possibility to detect this small. And in addition, you have to remember, stars are rather faint. You don't have so many photons. So this technique is to use, if you can, the whole domain of wavelength and to use the total information, Doppler information, in these thousands of lines to detect this very, very small change of the velocity. And during the last 40 years, 50 years, I don't know, you see that a lot of progress was made. You see, if 50 years ago we were with the capability to have a measurement of 300 meters per second with this technique, 20 years ago it was something like 1 meter per second. This instrument is still in operation in Chile, but the last instrument of this series achieved just the limit to detect the reflex motion, the wobble of a star like the Sun, induced by a planet like the Earth. But as you have seen before, stars do not help us because you have a lot of difficulty. You have acoustic mode, the stars like the Sun are vibrating. You have dark spot, and you have a granulation due to the fact that the outer part of the star has a convective region. So you have gas going up, very hot, shining, and going down, and so on, with a velocity of something like 1,000 meters per second. And you are dreaming to measure the velocity, the change of the velocity of the star, the mean of all these atoms, to a precision of something like 0.1 meter per second. This is, you have seen before, this is really the problem we are facing. Yes. A few years ago, a young colleague, one of my young colleagues, developed a small telescope of 10 centimeters. And observing the velocity of the Sun every day with the same instrument we are using that night to measure the velocity of stars. And this is the apparent velocity of the sun as a function of time. You see these days, and you see the apparent velocity of the sun changing, but more than 1 meter per second. So much, much more than what we are dreaming to detect Earth-type planet. This is a view of this small telescope. Very, very, very not evident telescope, because it's not a problem to measure a small part of the sun, but to measure the mean velocity of all the whole sun. So this is the most recent object. A lot of my colleagues in different institutes try to develop software tricks to eliminate the noise coming from the magnetic activity of the sun. You have a lot of different approach for that. And this is only one of them, made by one of my young colleagues. Here, if you select lines by the level of formation in the atmosphere of the stars, and you see that the lines, the smallest line, are changing quite a lot of velocity with time. If you are looking on much larger lines, you see that the change of the velocity due to the convection is much smaller. So if you select only, you try to correct for this object and select mostly the line with the smallest variability, or you correct for the effect. In fact, you can dream to approach a velocity less dependent of the magnetic activity. And this is a diagram obtained quite recently by a PhD student in Geneva, and this is related to the sun velocity. And here this is a periodogram, so the analysis of the frequency or the change of the velocity of the sun. You see that here you have an excess of power in the domain of the velocity of the rotational velocity of the sun, because you have spots and so on, but you don't have only one single velocity, but because you have a differential rotation on the disk. This is half the velocity, and if you apply the technique previously mentioned, you can diminish the noise to 0.25 meter per second. So it's not 0.1, but we approach, because the crude RMS of the change of velocity is much, much larger than 1 meter per second. So this is very important reason to be optimistic that in the future we can detect very similar objects to our own Earth, evidently because we are dreaming to detect life. This is just to see the power of this kind of algorithm, because here, if you have the amplitude of the wobble of the velocity as function of the period, here, days, 1, 10, 100, 1,000 days, all the object previously detected by Doppler technique was a dark spot, these dark points, and with this new kind of algorithm and technique to analyze the spectrum, you see that quite a lot of new planets have been detected. So this is typically the dirty part of this kind of research. And evidently, obviously, you need to have a lot of photons, because to have a chance to detect this very, very small change of velocity, you need a lot of photons. And this is the reason why a couple of years ago we have developed with a large consortium, when we say we, it's several institutes, have developed a large spectrograph with the instrumental precision of over 10 centimeters per second, and connected to 4 8-meter telescopes, so the equivalent to a 1 16-meter telescope on top of Paranal mountain in Chile, north of Chile. So a new techniques is really important in terms of complement to this one. And this open a new field is what we call comparative planetology. So to start to do physics of planets. And the idea is quite simple, that as we have seen that we have quite a large number of planets with short period, in fact, you have a good, relatively nice probability to have the planet orbiting. Here the planet is behind, here is in front, again. So when the planet is in front of the star, you have a decrease of the luminosity, and you have access to the ratio, the diameter of the planet compared to the diameter of the star. So you have the possibility to determine the diameter of the planet, but when the planet is behind the star, you have a diminishing of the infrared luminosity, so you can determine the temperature of the atmosphere of the planet. But what is the most interesting is this small ring here. This is the atmosphere of the planet. And the atmosphere of the planet acts as a filter of the luminosity coming from the star. So change slightly the spectrum of the star. So if you compare the spectrum when the planet is behind or in front, you have a small difference. And this is small difference give the information for the chemical composition of the planet itself. This will be the most important domain of research in the domain of planetology during the next 10, 20 years. And for example, the James Webb Telescope just ready to procure, to give new kind of data and information will be really concerned with this kind of technique, what is transiting spectroscopy. So this is an historical object by this technique. You see this is the first measurement made. We have detected a planet with a period of 3.5 days. So as for many we tried, if by chance the orbital plane is convenient to have a transit, and we were collaborating with colleagues in Boulder, and you see sometimes people don't like to have big telescope. This was only a 10 centimeter telescope in a garage made by Tim Brown. And exactly at the time expected from the velocity change, you see the drop of the luminosity when the star was in front of the planet. No, planet in front of the star. And you see that the diminishing is about 1–2%. So the size of the planet was about 10 times smaller than the size of the star. So you have access to the diameter of the planet. And they have repeated the same measurement the next season with the Hubble Space Telescope. And you see when you are out of the atmosphere, the quality you can achieve. So immediately, if we can have such a beautiful precision when you are out of the atmosphere, maybe we can detect much, much smaller planet by this technique. Maybe you can notice if you have the mass and the size of a sphere, you can determine the mean density. And the mean density is 0.3 gram per cubic centimeter. So it's less than the density of water. And just to compare, the density of Saturn is 0.7. So it's more diluted than Saturn. This was a direct proof that it is really a giant planet. And then after, obviously, this technique was offer a fantastic development, as this is the harvest of the Kepler space mission. It's not the total, this was a document in 2013, but most of them was already here. And this is the radius in unit of Earth radius versus the period in days. And evidently you are not so sensitive to object in that region. It's not real, but it's due to the sensitivity of the technique. You see the huge number of objects detected by this space mission. The idea of space mission is absolutely fantastic. So you have a star, you have Kepler. Look this in that direction, one small part of the sky, and orbit like this during several years. Every few minutes, you take a picture of more than 100,000 stars, small part. At the end, you have a long series of measurements for a huge number of stars, and you analyze with a computer. And you can find this object like this, and still more complicated. For some of them, you have things much more complicated because you don't have only one planet, but you have several planets orbiting the same object. And if you consider the colors, for example, you have here object in red. Here, this corresponds to object stars with 6 planets orbiting the same stars, and so on. So you see, multi-planetary systems are extremely common in the universe. Now, I like very much, it's a little bit more tricky, but it's interesting. How you can use this kind of technique to determine the chemical composition of planets. As you have seen before, this small blue ring filtering the luminosity of the star. So, let's imagine you have a color, a wavelength, where you have a very strong absorption. So the light will not enter in the atmosphere of the star, so the apparent size of the planet will be large. At the opposite, you have a different wavelength when the optical depth is such that the luminosity can enter very deep in the atmosphere of the planet, so the apparent size of the planet will be much smaller. So simply considering the contrast of the transit is a measure of the chemical composition of the planet. And this was applied many times. You see here light with a strong absorption or small absorption, and you see this apparent size change. And this acts as a spectrograph. And this was developed, and I can add right now a much, much longer list of detection. So we can start to analyze the chemical composition of planet. You still not have seen the planet, but you can enter this kind of details. And once again, the James Webb can do this very well in the next decade. But, okay, the James Webb is a beautiful object. I'm sure that it will provide a lot of interesting quantity, but have a look at this diagram. When I did my study a long time ago, the most famous telescope was this one. It was the Hale telescope, 508 meter telescope here. And this is the last project with the ELT with 39 meters of diameter. And you can see here. And you see the huge increase in size provided by the technology of telescope and optics. This is the present development status of this instrument in north of Chile at 2,800 meters. This was the status the 1st of January of this year. Mostly the basis was existing. And you see this is absolutely huge. Maybe you can see the two people here. No, here. This is really a fantastic telescope. I hope we can also observe quite a lot of interesting for that. Evidently, as mentioned before, the James Webb already with fantastic images obtained the last 2 weeks. And all this effort to search low-mass planet, Earth-type planet, are devoted to the problem. It's a very important question. Is life a cosmic imperative? Is life some kind of an automatic process of the evolution of the universe when the conditions are evidently present? And this is certainly the big challenge for the future, for the next generation. And the idea, I will not speak on this domain, but just mention this will be to adapt the technique developed before on this spectroscopy of transiting planet to get inside in the chemical composition and specifically to detect what is called biomarkers, so signature of life in the atmosphere of this planet. So this is a fantastic question for the next generation. So, up to you.
Thank you. I have a demonstration in a moment, but let us return to the universe on larger scales. You've seen this, and I draw your attention to something peculiar about it. As you know, one may look at the world around us on many different scales. You may study people. You may study the cells within a people. You may study the molecules within the cells. You may study the atoms within the molecules. You may study the atomic nuclei within the atoms. You may study the quarks within the atomic nuclei. Level after level of things to look at. And you saw with increasing scale things to look at. Planetary systems within galaxies, within groups of clusters of galaxies, to this. And the interesting thing here is simply that. As we increased the scale, we did not see something new. This is the universe on large scales. This is the pattern of distribution of matter in the universe. And you notice, whoops, this side, this side. This is the picture of the universe on the largest scales we can attain. It looks the same everywhere. That is a deep, it's rather a fundamental point that is difficult maybe to appreciate, but it is a change from all of the levels of hierarchy of structure that we know so very well. Now, this universe is expanding. Here, a charming image of Albert Einstein and the astronomer Willem de Sitter at the Leiden Observatory in the Netherlands. Einstein, 1915. During the depths of the First World War, Einstein, contemptuous of that ridiculous operation, many of his colleagues enthusiastically supporting the German side, yet Einstein's prestige so great that he could continue to think about the nature of gravity. He invented a theory, the general theory of relativity. That theory was startlingly successful. Next to him, Willem de Sitter, Willem de Sitter was one of the first to appreciate the elegance and the beauty and the potential application of Einstein's relativistic theory. 1917, 2 years after that, Einstein decided that a philosophically satisfactory universe would be the same everywhere. He had no right to guess that, as Willem de Sitter told him very sternly. Yet Einstein was not one to abandon elegant ideas. He stuck with the notion that the universe is the same everywhere. Here is an example of what Einstein had in mind. Pretend for the moment that you live on the surface of a sphere. You live in 2 dimensions. You must not ask what is above the surface or below the surface. You don't live there. You can't ask that question. Instead, you live on this surface, and you notice that if you walked in one direction, you'd come back to where you are. Here is a universe that is the same everywhere, and yet it is finite, because space is curved on that surface. Imagine, if you could, 4 dimensions, a balloon of 3 dimensions, that's where we live. You mustn't ask what's outside the balloon of 3 dimensions. You only live on the balloon. I will talk in a moment about the expansion of the universe. And I think it's fun to look back and see how things developed and how we got to this notion of an expanding universe. You see on the far left, Percival Lowell. You may know the Lowell family of Boston. There's a famous poem. So now we are in Boston, the home of the bean and the cod, where the Lowells speak only to Astors and the Astors speak only to God. He was one of those Lowells. He had a great fortune. He decided in middle life that there might be life on Mars. And if there were life, then he felt they would be digging canals, because that's what people did in those days, big engineering. He used his fortune to build an observatory to look for canals on Mars. Astronomers celebrate his memory because he chose to build the observatory, put the telescope at a site that is good for astronomy, not convenient to get to. A site in Arizona, Flagstaff. He also decided to hire competent astronomers to instrument and use his telescope. In particular, he hired Melvin Slipher. Melvin Slipher developed the technology to measure the effect of motions of galaxies. You all know the Doppler effect. You stand by the side of the road, the car passes, boom. Right? The burr, the higher tone, because the car is approaching you and the sound waves are squeezed to shorter wavelength, higher pitch. Start moving away, longer wavelength, lower pitch, boom, burr, boom. So it is with light, and so it is that Melvin Slipher discovered with the galaxies that I showed you earlier. Their light, of most of them, is shifted toward the red. Next, Henrietta Leavitt at the Harvard College Observatory. At the time, women were not so appreciated, but she got around that, and she developed the means of measuring distances to stars by using the Cepheid variables that are so important today. She showed how to measure the distances to stars, hence the distances to galaxies. Edwin Hubble in California, then at the Mount Wilson Observatory, used Slipher's velocities and Henrietta Leavitt's distances to see that an interesting effect. The more distant the galaxy, the faster it's moving away. Let's pause to think about that. Imagine, and I should have forgot to mention, this is Professor Dr. Willem de Sitter. It's a lambda for reasons I'll get to. It's a lambda backwards, I don't know, artistic license. It's a pretty good representation of his head, would you say? And the rest, well, artistic license. Imagine that this balloon is being blown up. It's getting bigger. The distances between the galaxies is increasing. You must not think that the galaxies themselves are expanding. Our galaxy of stars is not expanding. You and I are not expanding apart from biological effects. But the distances between the galaxies are increasing. And you notice an interesting effect. I sit on a galaxy, and I look at this one, it's moving away. I look at this one, it's moving further away. It's moving faster because it's further away. A nice formula emerges. The rate of motion of the galaxy away from us is directly proportional to the distance. Hubble's law. Here it is. These were the data Hubble had in 1929. He said, wow, recession velocity proportional to distance. I'm not sure how far that would get today. But in the next few years, Hubble, with his assistant Hubminson, got out to recession velocities of 10% of the velocity of light. Wow. And in these deeper data, it's very clear Hubble's law is a very good approximation. Recession increases with increasing distance. I keep pushing the wrong button, but never mind. It's interesting to note that this is 1930. Yeah, 1936. I was 1 year old. The next factor of 10 in recession velocity took until, well, from the late 30s until the late 2000s. Sometimes you make advances quickly, sometimes slowly. Now let's look at a few of the people who've developed the theory of this expanding universe. The first person I know of was the German Hermann Weyl, who had hints of the idea of this expanding universe and its connection to what the astronomers were seeing. The Russian Alexander Friedman carried the theory much further. He developed the theory of an expanding universe, but unfortunately he developed a little earlier than appropriate because he didn't have the data. The Belgian Georges Lemaitre, in the year 1925, had the theory and he had the data. That's the magic thing. Independently, he discovered the theory, published that in 1925. No one noticed. 1927, he put together theory and observation and published it, and no one noticed. But after a great struggle to attract the attention of the good old boys, of the old boy network, it was recognized. It was Lemaitre who really had the vision of the expanding universe. So what's next? The universe, we are now convinced, contains a sea of radiation. It's at microwave wavelengths, rather like your microwave oven, centimeters in wavelength. This radiation has the property of thermal equilibrium. You're all familiar with thermal radiation. You stand by a bonfire, you put out your hands, they're warmed. That's close to thermal radiation. Put that fire in a cavity, keep it somehow supplied with oxygen, and let the radiation relax to thermal equilibrium, bounce around, mix up. It relaxes to a statistically steady state. That state, thermal radiation, is a nice property. You tell me the temperature inside that cavity, I'll tell you the intensity at each wavelength. That's illustrated here by different thermal spectra. These are kind of hot. I'm going to go down to a couple of degrees above absolute zero. So a deep question arose once one had detected this radiation. Namely, is it really have a thermal spectrum? Two groups worked on this problem. Here is one. They were associated with the US NASA program. They obtained brilliant results, and John Mather here obtained a Nobel Prize for his work in at last measuring that spectrum and showing that it's wonderfully close to thermal. Here is a second group working on the same problem. The NASA group worked for 15 years to develop first the approval for the mission, then the plans for the mission, then the creation of the instrument, than the satellite measurement. In the year that the proposal for the NASA group was first created, this person, Herbert Gush, University of British Columbia, Western Canada, flew the instrument that would ultimately detect this radiation and measure the spectrum. He flew it in a rocket, but he had a limited budget, and he couldn't afford to put enough shielding around the detector to keep ground radiation away from the detector. So he had a flight, but it didn't succeed. He had a later flight that was almost successful. Rocketry is a heartbreaking business. The rocket was sent up, and you know the instrument package is at the head of the rocket, and after the fuel in the rocket is expended, a little explosion will push the instrument package ahead of the rocket. Now, this is a solid fuel rocket, and one of the hazards of a solid fuel rocket is that not all the fuel burns. And in this case, what happened is the fuel reignited, shot the rocket ahead of the instrument package, and sprayed it with horrible chemicals. A heartbreaking job. But in the year, well, I mean, this is really, I hope you're heartbroken. Never mind. In the year, what am I saying? The two groups obtained finally results. Oh, well, I should have introduced you to the rest of Herb Gush's team. Here he is. The white jacket, it inspires confidence, right? Notice his two, this is an image that I love above all others of scientists at work doing something really great. Mark Halperin, on the left, Ed Wishnow, examining part of the instrument. And I love to ask people, if you didn't know that these people were part of something great, if you had only this image to judge them by, would it inspire confidence? I think there is a lesson there for us all. So, within months of each other, after that enormous span of time and development, the many attempts with the rocket, these are the results obtained. Either one of them would have made the case, yes, this radiation is thermal. The universe as it is now is optically thin. It is not going to make thermal radiation. This spectrum is tangible proof that dinosaur footprints are tangible proof that those improbable creatures walked the face of the earth. This is tangible proof that the universe passed through a different state, one which was dense and hot enough to have produced this thermal radiation. It is a milestone in the history of science, a simple picture, but with the deep implication that our universe is not forever. Again, we see Professor Dr. Willem Sitter and his balloon. Now, it's in a little side story. Einstein, 1917, decides that a philosophically sensible universe will be the same everywhere. He had a theory for gravity that he trusted and that I wouldn't have at the time, but in fact has proved itself to be very accurate. In this theory, universe structured like this, with mass in it, will collapse. Gravity pulls things together. He was distressed at this and finally came up with a solution. He introduces a new term into his theory. That term acts like repulsion. So he has what came to be known as Einstein's cosmological constant. It pushes. Gravity pulls. Choose the right value of the cosmological constant for the density of the universe. Bob's your uncle. It's stable. But of course, you know that's not stable, because if you shrink it a little bit, then the repulsion, the attraction is bigger, and the repulsion, therefore, doesn't work and it collapses. If you make it a little larger, then the repulsion dominates over gravity and it expands. This is an unstable situation, very unsatisfactory. When Einstein learned that the the evidence of the universe is expanding, he said, away with the lambda. We'll see the results in a minute. Anyway, I just paused to remark that for many years, one of the great goals of astronomers was to see the effect of this cosmological constant. We need to go into any of the details, but I'd love to show this image because these three, I very seldom see them looking so neat. They are receiving the Nobel Prize for their work in the demonstration that the expansion of the universe is now increasing due to the effect of Einstein's cosmological constant. A remarkable result. So let's go on and consider Einstein's thinking about that cosmological constant. Here is Georges Lemaitre visiting Caltech. Here is Albert Einstein. If you have really good eyes, you can see, you see his Einstein signature? It's there. If Lemaitre signed his image, we're never going to see it. And Millikan was just the president of the university. These were the two real big actors. In the years following the Second World War, 1947, Georges Lemaitre had convinced himself that there's a lot of good to be said about the cosmological constant, not from the evidence that came much later, but rather just from the character of the cosmological constant. We'll not get into any of the details, but you see here he has written a letter from Brussels to Professor Einstein about an essay he's going to contribute to a book about Einstein's philosophy of science and life. July 30th, 1947. Here is September 26, 1947. Einstein at the Institute for Advanced Study has replied, "Thank you very much for your kind letter," and on and on. He's being polite. Here's more on the letter. Oh, where is it? You see at the top in the there is a reason to try bold extrapolations and hypotheses to avoid contradiction with facts. It is true that the introduction of the lambda, that's Einstein's lambda, term offers a possibility. It may even be that it is the right one. You see from the next paragraph that Einstein was being polite. Since I have introduced this term, I had always a bad conscience. Go to the bottom line. I cannot help to feel it strongly, and I am unable to believe that such an ugly thing should be realized in nature. Well, you see, even the greatest of scientists can be fooled, and the rest of us are not so great. We're fooled very often. But of course, we are set straight by something wonderful, measurements that can check theories. I talked about a measurement now, and I have brought along a sophisticated experiment. Perhaps you remember this from your youth, or some of you are youth, so perhaps you still do it on occasion. Isn't that lovely? We know what's going on. This is short, so it makes a short wavelength wave that fits inside here. It's a high pitch. This is long. It fits a long wavelength node of oscillation. It's lower pitch. It's an example of the boundary condition imposed on a fluid when it's shaken. Fluid or a gas, I should say. When shaken, the boundary conditions, the wave has to fit in here, determine its frequency. So it is with the expanding universe. In brief, the early universe was hot, so hot that electrons are stripped off atomic nuclei. You had at that time a soup of electrons, their ions, the atomic nuclei, and radiation. The electrons scatter the radiation. The nuclei, which are charged, scatter the electrons. The result is that electrons, ions, and radiation are coupled together and act as a fluid with a pressure. shake that fluid, and the universe being not exactly uniform, as it expands, this fluid oscillates. The oscillations stop at a definite time when the temperature is dropped to about 1,000 degrees Kelvin, and the electrons attach themselves to the ions. The electrons are no longer scattering the radiation, so the oscillation stops. It's the same game, boundary conditions. In the case of the universe, boundary conditions in time that set waves that are characteristic of a universe that's expanding and cooling. So let us have a look very briefly at the result. Okay, well, this I worked out with a graduate student in late 60s. I thought it was an intellectual exercise, but it was observed. Up above, the pattern introduced in the distribution of radiation across the sky, patterns of oscillations as a function of wavelength. Down below, the distribution of galaxies. The solid curves, the theory. The spectacular fit of theory and observation is to be wondered at and admired. You don't get a good fit at long wavelengths because the waves are too big to fit inside the part of the universe we can observe. Admire, please, the spectacular consistency of theory and observation to the right hand of the part of the upper diagram. Down below, because there are far fewer galaxies than bits of radiation, the measurements are much noisier. But what's really spectacular from my point of view is you get the same theory fits both kinds of data. Above, measurements of the temperature of this radiation across the sky, tiny fluctuations, but with that pattern built into them. Down below, spatial distributions of galaxies. You're looking at two wildly different things, and you're finding a consistent story. Wow. It's that sort of consistency that by which you judge the reliability of a theory. This consistency, with other tests that we need to get into, convinces me that we have a pretty good story. I should emphasize that, sometimes we physicists can be arrogant and make flat statements. We really shouldn't ever do that, because we will never have an absolutely perfect theory that we know is perfect, because we know a theory is good when it fits the measurements, that passes the tests. No test, no measurement is arbitrarily good. Therefore, we will never be able to convince ourselves that we have a final theory. That's just life, just as we'll never be able to look at all the planets in that nearby galaxy I showed you. But we can get very good approximations, and we can actually ask ourselves, well, where did it all come from? And I'm going to answer that. Consider this. The world is full of a number of things. I'm sure we should all be as happy as kings. You have seen examples of all the wonderful things that are in our universe. And we should all be very happy with that. And although we will never know, I think, it's my guess, we'll never know where it all came from, but we will be happy as kings because there is so much we can look at and admire and study. Thank you.
Thank you very much, Jim. Thank you again, Jim. Thank you also, Michel, for your presentations. That was really a privilege to hear you talk about your work. I think we can give a second round of applause because this was really inspiring. Please have a seat. Please have a seat. Over here. Oh. So we'll now be moving to the second part of our panel, of our event, with a panel discussion. Yes, you can see just over here. Perfect. And for that, we'll be having on stage other experts coming directly from Switzerland. And first, I'd like to welcome Professor Richard Anderson, who needs no introduction. He's one of the organizers of the event. And to follow, we have Professor Michaela Hirschman, who is a tenure-track assistant professor at EPFL and the leader of the Laboratory of Galaxy Evolution and Spectral Modeling. Her research is focused on cosmic evolution of galaxies and their supermassive black holes. And last but not least, we would like to welcome our Swiss astronaut Claude Nicollier, who flew on board the space shuttle 4 times and also studied astrophysics alongside Michel. Thank you very much, all of you, for being here tonight. We've had an eye on the history of cosmology and astrophysics, but for this panel, why not looking ahead? And my first question would be for you, Jim. What do you think would be the next biggest breakthrough in astronomy for the next 10 years?
Wouldn't you say it's a JWST telescope?
That may be one of them, yes.
You pause to think that the Hubble Space Telescope had the wrong focus when it was launched. A horrible blemish on NASA. Such a blemish that NASA went to great effort to discover the anomaly, to fix the corrective lens, and to go up there and install it. What a gem. Wonderful, wonderful example of technology with great care. But now, JWST is beyond the ability to repair. It has so many moving parts. Any one of those moving parts fails, and the telescope is next to useless. It's such a horrible thought. I could never stand to have a hand in JWST. Science and engineering is wonderful, though, and that telescope is now in position, and it looks like it's going to be a great success. It's a general rule in life. You look in a new place and you'll find something new. Not very surprising, but important. Time and again, we've had an ability to look at the world in a different way, and we found something we didn't expect. My bet is we're going to be surprised once again. It's also, of course, my deep hope.
Thank you,
Where
Jim.
are you? Oh, there you are.
We happen to have one of the people who actually repaired the Hubble Space Telescope and followed the James Webb, JWST, James Webb Space Telescope very closely. Claude, what are your takes on the next 10 years in astronomy?
Well, it's going to be amazing. I mean, so many incredible instruments. The Webb was mentioned. We have the EELT. Many other instruments now are being developed and used, and that's going to be an incredible gathering of data about so many things in the universe. I have to say, Jim, that there is something that bothers me a lot still. You showed this beautiful picture of Messier 101 spiral galaxy, and you mentioned how beautiful it is, and I concur that it is really aesthetically beautiful. But when I think that what we see is about 15% of the mass, and the rest is the dark matter, and I think this is one of the biggest challenge. There are many others, but one of the big challenges of the next 10 years of astrophysics, the dark matter. What is it?
Michaela, your research is focused on cosmic evolution of galaxies and supermassive black holes that were on the news quite lately. What do you think will be the biggest questions answered in the next 10 years?
Yeah, so I mean, I agree to some extent that, I think with James Webb, we will be really probing the earliest cosmic times with higher sensitivity compared to like any other telescope ever before. So I think that with this telescope and also, other revolutionary instruments, perhaps like SKA or also ELT, which was mentioned, I think that we're going to get new discoveries how the first stars and the first galaxies in our universe may have formed just a few hundred million years after the Big Bang. And So I think, comparing these data then to model predictions, I'm very excited what we will learn about that. And in the same direction, I think we will also get to learn about the formation scenarios of supermassive black holes. We know that these supermassive black holes, they're there in the galaxies, but we don't really know where they actually come from. And I think already with James Webb, and then also later on, perhaps with the Athena X-ray telescope or some gravitational wave interferometer LISA, we will really get, a deeper understanding of how these monsters in the galaxies may have formed. And I'm looking forward to that.
I think we're all. And if we look towards a more specific aspect of astronomy, we've talked about exoplanets that we discovered 25 years ago, Michel, thanks to you. And we've made tremendous progress since then, but we still haven't detected life. Do you think that if life is indeed universal, we will be able to detect it by the end of the century, let's say?
Maybe we can wait. No, I don't know. I'm sure it's difficult because the change we are looking for the Bayer signature are very, very small. And it's only when you will have detected quite different signature that you have some hints that probably we will have life. So I do not believe that this will be discovered in the next 5 years or so. It's really a long-term work. But I will just add something to the previous question.
Feel free.
I dream that the best new discoveries on the next 10 years will be something that we are not looking for today. But let's imagine that nobody believed 20 years ago that the expansion of the universe will be increasing velocity. So sometimes you receive something completely new. So for me, this will be the best we can dream.
What we all hope for.
Yes.
And what about you, Richard? Any takes on the future of astronomy or detecting life on exoplanets?
I believe that astronomy is just such a huge subject. We have literally the entire universe to study, and we're bound to be surprised, as Michel has just mentioned. One of the subjects that hasn't yet been discussed here today is, for example, the makeup of our own Milky Way. And we're now really teasing out the structure, the motions of the stars in our Milky Way, and how over time our home galaxy has been, created, but in a very chaotic sense. And for example, the Gaia mission is really just phenomenal at providing information about this 6-dimensional phase space and telling us how this wonderful system that we live in came to be.
Amazing. But we also have a lot of work to do already in our solar system, right, Claude, to detect life? Claude, to detect life in our solar system, we still have a lot of work to do, right?
Yeah, well, I think the detection of life in our solar system using robots and rovers is very important because we've heard about the possibility to detect signs of life in the atmosphere of exoplanets. Michel mentioned that, and it will even get better with the James Webb detection capability. But if we find indication in the atmosphere of an exoplanet that there may be life, it's going to be really difficult to be absolutely sure that there is life. But in our solar system, whether it's on Mars or on Titan or Europa in the water under the sheet of ice or Enceladus, I mean, there are places in the solar system where using rovers and the robotic techniques, we need to get closer to trying to find signs of life, whether it's past life or present microbial life in the solar system. I think this is a very important field of studies over the next decades, I would say. Find real signs of life, existent or past, in the solar system.
Yes, please, Michel.
I fully agree with this. Good. Let's imagine, I don't know, maybe 20 years, you have a spacecraft picking part of the ice on the break of the ice shield of Europa. You don't need to dig, it's so impossible, it's too deep. But when you have a crack due to the tidal interaction between satellites, some water is coming from below, arrive, and immediately ice here. So let's imagine you pick 1 cubic meter of this ice, eat it, filter, and you find something. So it will be so much more exciting than exoplanet. So, because you will have a chance to look on the DNA. Is it the same as ON1 or not? So, future is beautiful.
It seems like we have a lot of challenges ahead, and as you said, we're bound to be surprised. But looking at our understanding of the universe currently, Jim, can we see its limitations already of our understanding?
Oh, limitations. Oh, absolutely. You have down here a question about inflation. So it's an interesting point. We have a pretty convincing story of how our universe expanded from a hot, dense state to the present, because that expansion left fossils that we can detect and interpret. But one can ask the question, what was the universe doing before the Big Bang? What does that even mean? The most popular idea is that the universe went through a phase of inflation, and before that it was a part of a universe that was also inflating. Wonderful ideas, and it's great to hear them debated and discussed, but you know, there is an absolute limitation. We build science by testing theory against observation, observation against theory. That is why we decide that now general relativity theory is not simply the invention of a very clever person. It is a good approximation to reality because it has been applied in many different circumstances. Recall merging black holes detected by their production of gravitational waves. All that evidence tests and general relativity, and the relativity passes. The definite limitation, go back far enough in time and we don't have any more tests. We don't have any more fossils. Inflation is a wonderful idea, but we must be prepared for the fact. You see, we must be prepared for many facts. One, you will never get to examine all those planets on that distant galaxy, on that galaxy next to us. You will, I think, never get to understand where the universe came from and what does it all mean, because we will not be able to see far back past the hot Big Bang into what the universe used to be like. We have been spoiled by the vast progress in science that convinces us time and again we have a problem, we resolve it, we make progress time and again. But there's no guarantee that will continue. And I think if we pause to consider the limitations, we know that that advance cannot continue indefinitely far. Different limits apply, of course, to different lines of research. I don't think in anyone's lifetime here will understand how your brain works. It can be explored, and it will be. That's going to keep people employed for a long time. The question, what was happening before the Big Bang, alas, is not in that category. It's easy to predict the situation to come. There will be a beautiful theory of what happened before the Big Bang. It will be consistent with all the evidence we have. It will make predictions, but we can't afford to test them. And so we will be forced to ask the question, do you really trust that theory of what happened before the Big Bang, or was it simply the invention of very clever people? We won't be able to judge. But there are lots of other things to look at, so don't be upset.
Michel, what are your views on the limits to our understanding of our cosmos?
Yeah, so I think, first I think that, our standard cosmological model really matured significantly over the past 50 years. from some vague speculation to almost certainty now. But I do see limitations, of course. I mean, we don't know what is dark matter, what is dark energy, which is kind of the basis still of this model, right? There are also other inconsistencies, for example, the Hubble tension. So Richard is an expert more on that. And there are also inconsistencies, you know, when we look at some cosmological simulations based on lambda CDM compared to some observations. For example, there's this long-standing missing satellite problem where people or simulators find way more low-mass galaxies around typical Milky Way-like galaxy compared to what is observed. And so this could also point towards, you know, some different form of dark matter as we currently assume. But I think that these kind of tensions and inconsistencies, perhaps we won't solve all of them, but I think that this is really driving science. This is driving of like the way we should go forward. And I would be looking forward to, or be curious, you know, how we will have been solving these issues in the next, I don't know, many years and what we have learned from it.
Thank you. And I want to ask a question to Richard, and it's the expert on the Hubble tension. Can you tell us more?
Yes, happily. The issue essentially is between our observations of the very early universe and the universe as it is today. So Jim was talking, of course, about the cosmic microwave background and the very early parts that we can observe there, and we can have a prediction for how fast space should be expanding today, so of that Hubble-Lemaitre law. But we can also measure it today, and this is what my research group is doing here at EPFL. We're measuring really the distances to other galaxies to then calibrate supernovae that allow us to measure how fast space is expanding today. So you're in a situation where you're confronting prediction coming from the early universe at a redshift of 1,014 billion years ago to how things are actually working today. And we see about a 10% difference between the prediction and what we see and what we measure today. And this is what is often referred to as this Hubble tension that could potentially, if it's real, and that's what we're studying here, would help us identify one of these cracks of the current cosmological model, and hopefully would be the first of probably multiple different ways of studying those cracks and thereby improving cosmology.
It's amazing to see that you all have huge career path. And well, my next question may be a bit more personal, but when did you decide that you wanted to become an astrophysicist or a cosmologist? Why did you do basic research? Maybe Michel, if you want to start.
Oh, I'm to go back to the time of my master at the end. We were working with friends, both of them on the same question, and it's the time we saw advertisement for PhD position in different, one at the École Polytechnique here, in statistical mechanics, and another one at Geneva University in astrophysics. So we discussed in the Lapin Vert, you know this. And we discussed, are you interested to go here or to me? And we chose, and both we went, and we stayed the full life in the position we had. And so maybe you know him, is Hervé Kunz. He was professor here at the École Polytechnique. So, why I would say that I was never chosen to do astrophysics. When I was kids and teenager and so on, I was interested in science. I was fascinated by every domain. And if in the Lapin Vert time we had an advertisement to do geophysics, maybe I will have done geophysics. Because geophysics succeeds to absolutely fundamental question in this time. You know, before the 70s, people do not believe in the plate tectonic. And it's only at the 70s when the people discovered that the pattern of the magnetic field was exactly the same on both sides of the North Galactic Ridge, that they understood that we have the plate tectonics. So in any domain of science, I believe we have exactly the same interest. So so if I chose astrophysics, it's only because at the good moment I saw an advertisement.
Great answer. Thank you, Michel. And what about you, Jim? Could you imagine yourself winning the Nobel Prize when you were 20?
No, no. You should bear in mind that prizes such as the Nobel Prize are awarded with great care. But nevertheless, they are awarded by people, and people will have to make judgments, which means that, well, to be blunt, the award of the Nobel Prize, it has to be capricious. There are many people who will appreciate, who merit the award than there are awards. You should therefore, if you are a student contemplating a career in science, you should not judge your career by prizes and awards. You should judge it by how you feel you have done, how you have contributed. The prizes and awards may come or not, but that's not why you're doing science. I've forgotten the question. Oh.
The question was, why did you choose science, basically?
Well, briefly, in high school, I was not a satisfactory student, I realize now, not because I was any way rebellious, but because I was, well, the phrase I think is appropriate, I was out to lunch. The result was I came to the University of Manitoba, not even realizing that there is an academic field called physics. That is where I learned that there is this academic subject and that it really, really attracted me. My professors at the university sent me to Princeton University for further work. I came thinking I'm going to do particle theory. But again, through pure dumb luck, I found a research group led by Professor Robert Henry Dickey, Bob to everyone, who was doing work in gravity physics that so fascinated me that I joined his group. Bob is the one who said, you should be thinking about cosmology. I was reluctant because cosmology was such a scant evidence. Barely, it was a science, but barely alive. So I wrote a few papers and thought, then I'll go on and do something meaningful, but one paper led to the next. You cannot plan ahead always.
And how about you, Michaela? Was it also luck?
I don't know whether it was luck. Perhaps it was luck because I got, when I was, 15, 16 years old, I got a popular science book in my hands about physics and astronomy, and it was fascinating me, like extremely deeply, so that I continued reading about that. And I didn't like physics much, it's cool, I have to say. But reading these books was like, well, yeah, that's what I want to do. So I want to study physics. And first, I was still hesitating, and I was doing my diploma, not in astronomy, but actually in condensed matter physics, working some experiment on some experiment. But then I decided, well, now for my PhD, either I do astronomy now or never. And so I went to Munich, to the observatory, and working there with Andy Burkert on a topic in cosmic galaxy formation evolution. And well, since then I stayed, and so far I haven't regretted.
Richard, it's obvious that astronomy, cosmology, if you'll hear, it's subjects that passionate a lot. But why is it important for society and humanity?
It's a very important question, and one that is also extremely difficult to answer. Sometimes people juxtapose the question of whether we should do basic science or solve real-world problems, but I really don't like to juxtapose it this way, because basic science drives our ability to solve real-world problems. And you don't know where exactly the breakthrough will come from. And so in a way, you need to chaotically explore all the possibilities, and you need to do it in a way that motivates people. And people are clearly driven to do basic research by their own personal interest. And if you allow them to do that and pursue that to the fullest of their interest, you will get the best results. And I think this is where basic research in general has a very important role for society, because you don't drive it, it's not application driven, but in the end it's going to define what your applications will be in the future.
Claude, you had the opportunity to go to space and see our blue planet with your own eyes. How is space exploration and cosmology astronomy important for society, in your opinion?
Well, it's very important, of course. Research done on low Earth orbit with the shuttle and now with the International Space Station is very valuable, because there is a look downwards, there is a look upwards, and there is taking advantage also of the local condition, which is microgravity, and there's a lot of experiments you can do. For instance, the behavior of the human body in weightlessness is really interesting, because you put suddenly the human body in a condition that is completely different from the condition that existed during the whole evolution of life for the last 3 billion years. And the reaction of the body to these conditions is very interesting, and that's an important field of research, not only in perspective of flight of humans in the solar system in the future, but basic knowledge about the physiology and the human body. And of course, going into space, it may be less for human spaceflight, because not a lot of astrophysics was done from human spacecraft with the shuttle or the International Space Station, but there's no doubt that access to space has been an enormous boom in capability to understand the solar system, the sun, the universe, and ourselves.
Thank you. And how about you, Michel? How do you think that astronomy and cosmology is important to humanity and society as a whole?
I cannot imagine the humanity without the curiosity. When you are looking stars, you are looking phenomena and so on. Can you imagine that you don't like to know what it is? For me, it's simply impossible. And in the past, you have to remember during a long time, people was afraid. When you have a comet, people believe it was frightening and so on. So I believe the astronomy is absolutely fundamental for the mankind, the curiosity
And talking about something that came up actually just last week, we had the first picture of a black hole in the middle of our galaxy. And Michaela, I know this is your area of research. Can you tell us what we learned from it?
Yeah, so actually I was extremely fascinated to have seen last week this, second image of a supermassive black hole in our own Milky Way galaxy. It's just so exciting. And so this has been taken, by the Earth-sized Event Horizon telescope, which is like a combination of different radio telescopes on Earth to increase the resolution, such that we could, for example, also detect a donut-sized object on the surface of Moon. And so what you see on these images is actually the shadow of the black hole surrounded by some background light, which comes from some glooming gas accretion around the black hole. And so I think there are perhaps two main milestones we got with these images. So the first one is that I think it's the most definite evidence that we do have supermassive black holes in our universe, in the centers of galaxies. And the second is then when you try to model the gas accretion around the black hole based on Einstein's theory of gravity, and you apply some sensitivity limitations, or as seeing through a telescope, then these simulators, these modelers, they actually managed to explain, to reproduce these observed images. And I think this is just a great confirmation of Einstein's theory, okay? That it also works in the extreme environment of a supermassive black hole. And I find this super fascinating. And they also said that they want to, continue measuring some of the black holes like for a longer time, such that they could make movies out of it, so that perhaps we can study even better how the gas is accreted onto the black hole. And yeah, I'm very excited to see more discoveries of the Event Horizon Telescope collaboration.
Chloe, may I ask a question to Jim?
Please do.
At some point you said our universe is not forever. And in fact, I see a question here which is from the public, and it goes in the same direction. Taking into account physical laws, what would be the most likely final state of our universe? In, I don't know, 10 to the 30 years, 10 to the 40 years, what will the universe look like?
We know a lot about how the universe has evolved because it left fossils. Physical evidence that can be tied into a theory that can be checked. The future hasn't left any fossils. And so I don't find it as interesting to think about what will happen as what has happened. There are ideas about the future. They talk about the big rip, the big freeze, the big crunch. It's all very romantic, but oh gosh, data one can test against theory is so glorious that that's what I love.
Thank you very much to all. I think we can now move on to the second part of our panel, where we will welcome questions from the public. So don't hesitate to use Slido. You can scan the QR code just up here. And we'll start with the first question with the most votes. What is the place of philosophy in astronomy and physics? Is there a volunteer to answer that question?
I didn't understand. What is the state of?
What is the place of philosophy in astronomy and physics?
Well, may I put in a shameless advertisement? Within a few months, there will be a book published by me. And it's a little embarrassing because every other book I've written, I've determined the title. But the people at the press, Princeton University Press, pressed me for a more exciting title, and I can't remember what it is. But it's all about the role of philosophy and sociology in physical science. You know, in physics, not only are we arrogant, but we always say, look, we're looking at objective reality. None of this personality stuff. It's objective. It's objective. It's real. It's objective. Of course, that's foolish. It's not the way we operate. We put our own personal opinions into our science. And this is a meditation on what you learn from the philosophers and from the sociologists about the way we behave in the natural sciences. There are no great revelations, of course. Natural science operates as it must, given the conditions, and the spectacular success is, of course, evident. But this thoughts about what we're doing from philosophers and sociologists, I think, are informative about the way we operate, and that's the nature of this book. So it's not very expensive. So consider it. It would be better if I could tell you the title.
Thank you very much, Jim. We'll be sure to find the title after the event. So if you want the answer to the question, you know where to find it. Moving on to our second question. I guess we've covered that already pretty much in the panel, but if someone would like to respond to that, how probable is that a man in his 20s... Okay, the question disappeared. Moving on to the third question. How do you estimate the chances of a human becoming interplanetary species over many billions of years when Earth is inhabitable? What do you think, Michel?
So, I'm not paleontologist, but I'm not sure that we know any species, living species, having been living on the Earth so for a few billion years. So in any case, I believe every species has some time life implied by the biology. So I'm completely orthogonal to this kind of perspective. And you have to always remember the distance between stars are completely out of we have in the solar system, for example. I have to repeat always my very simple arguments. Man went to the moon 50 years ago in 3 days. Light need only 1 second. Let's imagine that we will discover during this search for exoplanet a perfect planet for the constraint for life development, temperature, and so on and so on. Let's say a very neighbor, 30 light years, so only. It's at the scale of the Milky Way, it will be a neighbor. But 30 years is already 1 billion seconds. So this neighbor will be 1 billion times further than the moon. So it's not a small detail. It's not a matter to just accelerate a little bit. It's impossible. So personally, I'm absolutely convinced that we are living on this planet and we will not move to another one. So I'm unable to answer this question.
The point is, we talk about the solar system here. Because in a way, if we talk about billions of years, of course, the solar system will have changed a lot. First of all, are our descendants still going to be alive? And I have no idea about that. Billions of years is so long. You cannot really answer such a question. But I think at the time the sun will become slowly a red giant, I mean, the solar system itself will completely change. And Mars will not be like it is now, and Venus will possibly will be not quite inside the star itself, but its atmosphere will have been blown away. So the solar system will be completely changed in billions of years, like it was not the same at all billions of years ago. Yeah? So it's very hard to answer such a question. And whether we will still be as a species on the surface of that planet in billions of years, I have no idea. I don't even know in 500 years what will happen on planet Earth, or 1,000 years.
And I think this is one of the ways that physics and astronomy can help influence philosophy and society, because you are actually mapping out where these habitable planets may be and how distant they are and how we could possibly get there, or how long stars will be able to support life on a given planet. But here we go, and we have a climate crisis, and we have war, and we need to make sure that we take care of this planet so that we can survive long enough before we can think about interplanetary travel.
Thank you very much for these answers. I see now that Nico's question is back up, so I can start again. How probable is that a man or woman in its 20s will see a major breakthrough in astrophysics that will completely change his or her perspective of human life? Maybe Michaela, do you have a guess on that?
So first, thanks for adding woman and her. So I don't know. I think it depends what we will find. I mean, perhaps when we indeed, find a kind of unifying theory for gravity, quantum physics, which is opening something new we would have not thought of, like it was with general relativity or something like that. Yes, I honestly don't see it happening very soon, but. This is just my personal feeling. I might be wrong. I hope that breakthrough will be achieved earlier, and that something great will come out, but I'm not sure.
Thank you very much. Then for the next question, maybe to Jim, do you believe that there is a theory of everything?
Unfortunately, there are quite a few theories of everything. It's human nature to push ahead with the theories, and wonderful ideas appear. Very few of them turn out to fit observations and get selected. I believe that there will never be a theory of everything, because a theory of everything means you have to have a theorem, an exact theory. We can never establish an exact theory, because in my philosophy, that requires exact measurements, and measurements can never be exact. So don't be so ambitious. Find a theory, contribute to it, and the theory will grow, and it'll become tighter and tighter, better and better, and that's all we can do.
Do you have other guesses from our astrophysicist, or no? All right, next question. Gravitational waves open a totally new window. Can there be other new windows we can think of? Michel says yes.
Yes, you have the neutrino. You have very big experiment developed for many years to try to detect something coming from neutrino. I don't know. I believe gravitational waves is a much nicer window, but neutrino is another one. Yes, and the physics behind all we can learn from gravitational waves is absolutely fantastic. I am sure in the coming few decades, this will be a big chapter of astrophysics.
Thank you. Next question. What is your take on the fact that the universe, as vast and complex as it is, can be nevertheless modeled to a high degree of accuracy by few laws? Talking about modeling the universe.
Yes, that is not wishful thinking. We have the experiments testing the theory in great detail. It's wonderful. And you know the example of Einstein's general theory of relativity. He had practically no empirical evidence to justify that theory. He was happy with it because it is so elegant. That's not a very good, reliable criterion. Yet a century later, the theory passes deeply demanding tests on a broad range of scales. The universe is remarkably comprehensible. We cannot ask why, well, but it is.
Thank you, Jim. How... Please.
Some people have tried to compare the different physicists by what they bring to the knowledge, to the physics. And I was surprised that, and some very important people like Landau in Russia and so on. And I was very happy to see that Landau considered Newton's importance higher than the importance of Einstein, because Newton brings the idea that we can use physical law to understand the universe. Evidently today it looks much simpler, but I believe this was so important.
And we were never issued a guarantee that we could understand the world around us in any detail. We often say, well, the theory must be elegant, it must be self-consistent. But we don't know that the universe is self-consistent. We only experience the fact that it certainly operates that way. So we are building on assumptions, no guarantees, but we are testing them.
I think it is still fascinating that the Principia, the book of Newton, written in 1687, I think in Latin, has all the laws that can explain the motion of the celestial bodies in the solar system and the Apollo program and everything we do. Newton is fine. I mean, as long as we have velocities which are reasonable and gravity level that are reasonable also. Book written in 1687. This is really amazing. The genius of Newton and the applicability of its laws is unbelievable.
Yes. Again, he had no reason to believe that it was so good, but it turned out to be spectacularly so. But of course, Einstein crept in there with the orbit of Mercury, and with GPS, you need general relativity.
Yeah, that's true.
Of course, we can also add that even though the laws that allow us to describe this are relatively simple, we do have a huge wonder that is still left to solve, right? What is actually driving the accelerated expansion of the universe? What is dark matter? That is a huge component of our universe that is still waiting to be addressed, and I look forward to seeing lots of progress on that front.
Yes.
Yes, I was focusing more on the subject of the astronaut and spaceships in the vicinity of Earth.
Thank you all for your comments. Moving on to the next question. Is there a field in cosmology that could bring a breakthrough innovation to face our current problems, global warming friendly? So,
Don't know.
in global warming mainly.
It's all a responsibility, global warming. This is frightening. But then the war in Ukraine is frightening.
Yes, we're facing many challenges, and do you believe that maybe there is an application or a specific field in what you do that could help to resolve these problems? Maybe Richard?
I suppose often the way these things work is not directly, right? You don't do cosmology to solve global warming. But as you go and you do cosmology or you do physics, you develop techniques that find applications elsewhere. And so this, to me, probably one of the best ways of cosmologists or astrophysicists to helping solve these types of issues is by developing methods that can be applied elsewhere.
Maybe before we saw a question, but she moved away. So the question, is it worthwhile to put so much money in science, in astronomy, and so on? I believe this is a very important point because I don't know when the equation of the electromagnetism was written 150 years ago by Maxwell. I don't know if he was looking for television. and many other things. So the relationship between the fundamental science and what will happen 1 century, 2 centuries after is completely unpredictable. And you mentioned before the GPS as a byproduct. Okay, only working if you have the general relativity, and this is present for everything. You see dynamics. You mentioned also the importance of the law of gravitation of Newton and so on. So most of the fundamental science have a huge impact on our society. And if people doubt to put money in fundamental science, he has to first to remember this point.
Let's recall that the U.S. program to put a person on the moon in order to show up the Soviet Union used, what was it, 5% of the gross national product? An immense sum of money went into that program. Out of it came integrated circuits that gave us, well, your cell phone. That cell phone is a spectacular demonstration of the ability of scientists and engineers to control nature. It's just stunning. But it grew out of such things as that space program.
Perhaps I can add. Oh, is this not on? It's on. Okay. So I think that there's not really the need that you always have also new technologies or something like that emerging. I think the reason for astronomy is simply that it answers, I think, a major fundamental question of humanity, right? I mean, it tries to answer how did our universe form, where do we come from, and it's been always a major cultural part of society. And so I think we should continue doing that just to try to please the innate curiosity of humankind in this respect.
Good.
Yes.
Yeah, the universe is also an incredible laboratory, with values of temperature, pressure, and the physical condition that are impossible to reproduce on Earth. So it's a wonderful laboratory of physics, a natural laboratory of physics.
Well, if you're not convinced that we should put money and effort in astronomy or cosmology, there's nothing more we can say. Okay, we'll move on to the last question of the evening. How can our actual knowledge in biology help to detect life signs on exoplanets? Maybe this is for you, Michel.
No.
No.
No, I'm not biologist, so I cannot say. I'm not sure that some people believe that you can have a different kind of biology. So maybe we can confident in some basic rules. For example, what is the most important feature of life is the fact that it can be transmitted to a mother to his daughter, to her daughter. And this is made with a long chain of atoms, and this is absolutely the most fundamental point of life. And if you eat a little bit too much, you break you stop the transmission to the next generation. If it's too cold, nothing happens. It's too slow. So, and this, I believe, is not depending on the detail. I believe people have tried to imagine crazy idea of life and so on, but personally, I don't see, and many people don't see any possible to escape this fact. Carbon chemistry and to have a long chain to code everything in the way to function. So I believe the problem to detect life, I believe, has to keep these very simple things in perspective. And I don't know if the progress. I don't know if progress in biology can help to detect life. I don't know.
In the spectrum of the light from a distant planet, could you ever hope to see signs of these macromolecules of biology?
At short time, not.
Short time, not.
Well, thank you very much. I think if we should summarize this panel, we'll be ready to be surprised in the coming decades. And I would like to thank our panelists and the organizers of tonight, but also the audience for coming and listening to our amazing speakers. I will kindly ask you to remain seated, if possible, for at least a minute while our speakers leave, and you have the opportunity to have an autograph and picture, if you'd like, on the balcony. They just learned that, apparently, but yes, that's... And I think we can give a final round of applause for everyone. On peut dire, on y va?